Let's find a general solution to the repeated root case for a second-order homogeneous linear constant coefficient differential equation. So here's an example of such an equation. So y double prime is y double prime minus 4y prime plus 4y equals 0. So we just need to, since this is a constant coefficient equation, we can just write down the characteristic equation. And using our shortcut for doing that, it's m squared minus 4m plus 4 equals 0. Remember, the order of the derivative on y turns into the power on m when we do this, and then the coefficients stay the same. And then solve this equation. This one happens to factor. It's m minus 2 squared equals 0. And that means we get one solution, one real solution. M is 2. And each solution to the characteristic equation gives us a solution to the original differential equation. So we get a solution, y1 is e to the 2x. All right, but from our existence and uniqueness theorem for homogeneous second-order linear equations, we know that a solution in general is going to look like c1 times y1 plus c2 times y2 for some fundamental set of solutions y1 and y2. So we've found one member of a fundamental set of solutions, but we need to find a second one before we have a general solution. So how can we do that? I mean, our trick of using the characteristic equation only gave us a single solution this time. Well, remember, if you have one solution to a homogeneous linear differential equation, you can find a second solution by using reduction of order. So let's do that. Now, our trick for reduction of order was that your second solution should be some function, which we called u, times your first solution. So in this case, that's going to be u times e to the 2x. And remember that u here is really a function of x. Okay, so we're going to need to plug this into the original differential equation. So let's take some derivatives. So the first derivative is u prime times e to the 2x plus 2u e to the 2x. Okay, the second derivative of y2 is going to be u double prime e to the 2x plus, let's see, 2u prime e to the 2x. So that's the product rule on this first term in the first derivative, plus 2u prime e to the 2x plus 4u e to the 2x. Okay, now we can combine these middle two terms. So u double prime e to the 2x plus 4u prime e to the 2x plus 4u e to the 2x. Okay, now we need to plug all of this into the original differential equation. Remember, for this example, the original differential equation was y double prime minus 4y prime plus 4y equals 0. So let's plug all of these derivatives of y2 into this. We get u double prime e to the 2x plus 4u prime e to the 2x plus 4u e to the 2x. Maybe I should have factored out all of these e to the 2x's. Minus 4 times y prime, which is u prime e to the 2x plus 2u e to the 2x plus 4 times y, so 4 times u e to the 2x equals 0. Okay, now we can gather up all of these terms according to the order of the derivative on u. So for our u double prime term, there's only one, this one, u double prime e to the 2x plus, Now for our u prime term, there is, let's see, this one and this one. So and remember, we've already factored out the u prime over here. So we get 4e to the 2x minus 4e to the 2x. So that's nice. Those happen to cancel. And then for our u terms, there's 3 of them. There's this one, and this one. So we get, so remember we're factoring out u. We get 4e to the 2x minus 8e to the 2x. Don't forget to distribute that 4 over there. Plus 4e to the 2x equals 0. And this stuff in parentheses, that all adds up to 0. And remember, that isn't a coincidence. That should happen. We knew ahead of time that that should happen because that means we did our reduction of order correctly. Okay, so looking at this whole thing, what we get is u double prime times e to the 2x equals 0. So in general, from reduction of order, it's possible for this u prime term to survive, but for this particular example of reduction of order, it didn't. All right, now remember we're looking for u, so divide both sides by e to the 2x here. You get u double prime equals 0. This is going to be an easy equation to solve. So integrate once, you get u prime is a constant. Integrate again, you get u is a constant times x plus some other constant. And remember, we're just looking for an example of such a function u other than u equals 0. And so, let's make this d instead of c. We're just looking for an example of some function u that would work. So we can choose constants to make this as nice as possible. So we can choose, say, d equals 0 and c equals 1. And so that means u is actually just x. So remember, our first equation was e to the 2x. Our first solution was e to the 2x. Our second solution, since we're doing reduction of order, it was u times y2, u times y1. And so that means x times e to the 2x. All right, now I won't do the calculation, but these two solutions are linearly independent. So since we started with the second order equation and we have two linearly independent solutions, these solutions form a fundamental set, and so the general solution to this differential equation is y equals c1 e to the 2x plus c2 x e to the 2x.